Hi there, and welcome to this talk on how to train BERT 15 times faster. I'm Neil Conway, CTO at Determined AI. So if we look at the state of NLP today, I think there's two really kind of compelling trends. First, if you look at the rate at which model performance has been improving, it's really been an incredible series of achievements that we've seen. It seems like every few months there's a new model which is able to deliver a kind of amazing performance on NLP tasks. But simultaneously, these increases in model performance have seemed to come with an increasingly staggering increase in computational cost. So we have a graph here of the number of parameters of recent NLP models. And you can see that this is just increasing at a very, very rapid rate. And that doesn't even include GPT-3, which if you've been on Twitter recently, you're very familiar with. That's a 10x. That's 175 billion parameter model. If we put that in practical terms, approximately $12 million to train, or if we look at the environmental cost, more than 600,000 car miles worth of emissions just to train one instance of that model. That's not including hyperparameter tuning, architecture search, or the kind of many iterations you actually have to do to probably train models of that size in practice. So, NLP today is simultaneously really amazing results, but pretty significant computational cost. So, as an NLP practitioner, where does that leave us, and what kind of tools do we need? So I think the reality is that NLP today, the ability to really build modern NLP models, massive computation, access to massive computation is basically table stakes. And the challenge then is that, although the cloud gives us the kind of bare, compute resources, building a development environment where you can access those computer resources in a flexible, efficient way, rather and spend your time actually solving NLP problems rather than managing your compute infrastructure is a real challenge. And a lot of NLP teams that I know they need that computational capacity, but it's difficult for them to get access to it without spending a lot of time building out their own infrastructure and essentially doing DevOps and managing computation. So I think there's a real need today for deep learning platforms that enable NLP practitioners or deep learning practitioners to really focus on model training and to be able to train their models on GPU clusters of any size, on-premise or in the cloud, in a very kind of transparent and simple way. So in this talk, I'm going to tell you about Determined's deep learning training platform, which seeks to solve some of those challenges, to make it really easy to get access to massive amounts of computation and use those in a very transparent way as a deep learning practitioner. I'll give you a quick demo of Determined, and then I'll walk through a case study which talks about how we use Determined to improve the fine-tuning performance of BERT by about 15 times with very few changes to our model code. So I mentioned that Determined is a deep learning training platform. So what is that? Why might you need a deep learning training platform? So obviously there's a lot of excitement around tools like TensorFlow and PyTorch. And those are great tools for, I would say, the kind of basics of doing deep learning. So writing down your model architecture, expressing your training loop, describing how you want to compute your validation metrics and so on. But when we think about modern NLP development and the kind of challenges that you face, there's a lot of tasks that are outside the scope of tools like TensorFlow and PyTorch. So if you want to do distributed training on a GPU cluster, that's something that once you go beyond a handful of GPUs, you're going to need additional tools to be able to do. Hyperparameter tuning, be able to find better models automatically, is something that I think is a crucial capability that isn't typically included inside the tools like TensorFlow and PyTorch. As you start to think about, as you have more compute resources, you need to think about how to manage those resources and how to get the most out of that investment in hardware that you're making. And reproducibility and experiment tracking, I think, are things that are increasingly recognized as essential requirements that don't come out of the box with TensorFlow and PyTorch. So we like to think of Determined as sort of like a batteries included deep learning platform. You could try to go out and find 5 or 6 different tools to address aspects of the challenges that I talked about, and you could figure out how to integrate them, how to maintain that kind of platform that you've built. But with Determined, what we try to do is really build an integrated development environment, which includes all those capabilities out of the box. So you don't need to figure out, if I want to do one of these tasks, how to set up an additional tool, how to fit it into my workflows, and how to maintain it over time. So in terms of where Determined fits into the model development process and the ML kind of typical ML workflow, as I mentioned, Determined is really focused on model development and training. So we don't try to manage your training data for you, and we don't try to do labeling. We integrate well with upstream tools that do things like ETL and data prep and so on, tools like Argo and Pachyderm and so on. Once you have your training data set, really that's the point at which Determined is really focused, is building this development environment for you to train models, tune models, do architecture search, find the best model for your machine learning task in the most efficient way possible. And then once you have a model that works well for your problem, we make it really easy to export to a downstream serving tool. So tools like Selden, TensorFlow Serving, Bento ML, and so on. So you can really think of Determined as basically a platform that sits between your application framework, so tools like TensorFlow and PyTorch. You continue to use those to write your model, and your hardware resources, so typically a GPU cluster. And we are essentially sort of a platform that wraps TensorFlow and PyTorch and makes it easy for you to accomplish those additional workflows and get access to those cloud resources or on-premise resources in a very transparent way. So I won't go into a ton of detail about the architecture of the system itself, but just to kind of give you a brief sense of the capabilities of the platform, we start with a GPU-aware resource management layer. So we enable you to share GPU resources among a team of deep learning or NLP engineers. We have built-in distributed training, built-in hyperparameter search, both based on state-of-the-art techniques. Every workload you run inside our system, we automatically track and record all of the training and validation metrics for you and organize those into a database that you can access later. You get real-time visualization and debugging, integration with Jupyter Notebooks and TensorBoard, and we make it very easy to both work with external data sets and then export trained models to downstream systems. So one important design choice is that Determined doesn't run off-the-shelf PyTorch or TensorFlow code. We have an API that model developers need to adapt their code to. So here's an example of the Keras API. I'll show the PyTorch API in a second. And this is a trade-off. There are other systems that will basically run black box containers for deep learning workloads. But we ask you to sort of organize your model code and implement this API. In this case, you need to tell us your model graph, if you're using Keras, how to access the training data, and how to access the validation data. So hopefully that shouldn't be sort of exotic requirements. That should be pretty familiar for people who have built Keras models in the past. And the trade-off here is that because your code integrates into this API that we provide, we can then give you a bunch of this additional functionality out of the box without additional changes. So once you kind of fit into this API that we provide, then you get fast distributed training, hyperparameter tuning, GPU scheduling, automatic fault tolerance, and so on. So it is a trade-off, and we're aware that there's a little bit of friction there, but it's something that we've ported a lot of models to the system, and a lot of customers have worked with our APIs, and it's something that usually is pretty mechanical once you've done it once or twice. So great, so that's a quick overview of Determined and the problems that we're trying to solve. Now I'll give you a quick demo of how the system works. So I'll switch over here to the web interface. So Determined has two main interfaces, a web interface and a command line interface. So I'm going to show how to train some simple models using determined. So first of all, in the web interface here, we can see that I've previously trained a few other models, and there's one model training at the moment. This is running on AWS. Right now, we have 8 GPUs allocated to the system. But one thing that we'll see is that as new workloads arrive on the system will go ahead automatically and provision additional cloud resources as needed, and then we'll terminate those resources when they're no longer needed. So we can see here, these are the models that we trained. If we look at a model that we previously trained, let's say this is a CNN for the Safar 10 dataset, written in PyTorch. Here we are training a single model configuration. So what we call a trial, which is a model with a fixed set of hyperparameters. So we've trained this model, and we can see here the validation. So here we're showing the validation error. We can also look at the training loss, for example, or other kind of validation metrics. These get plotted in real time as the workload runs. And we can see the hyperparameters that were used for this particular workload. So that's a workload we previously trained. Let's go and take a look at how we train a new workload. So there's two main inputs to the system when you want it to run a new training workload. There's your model code and a configuration file. So as I mentioned, the model code is going to be your standard PyTorch or TensorFlow, Keras, or TensorFlow Estimator code, adapted slightly to fit into the APIs that we provide. So we can take a look at what that looks like. So here we have this is PyTorch code to implement a CNN for the Safar 10 dataset. So we're just using the kind of standard PyTorch APIs. We create a model and wrap it. So this is a API that we're providing that we're basically taking a standard model that you created and wrapping it so the system knows about that model architecture. Then we decided the optimizer, and that we're also going to wrap. And one thing in terms of the API, in the constructor for this class that you write, we're going to pass in this context object, which is going to, is a way for you to access a bunch of the information about the training context in which your model is running. So one thing in particular is that this is a way to access the hyperparameters. So the choice of hyperparameters for your model is totally up to you. As the model developer, it's really, what are the knobs that you think are going to influence model performance. So they can be everything from properties of the optimization procedure, like the batch size or the learning rate, to things that affect the model architecture, to aspects of the data preprocessing or data augmentation. And it's totally up to you how you use those hyperparameters. So we have no kind of semantic knowledge of these different hyperparameters. It's just up to you to say, you declare those hyperparameters, and then you plug them into your model code however you like. So in this case, for example, we're setting our layer 1 dropout, and that's being plugged into the model architecture in the appropriate way. And then, so that's how we create the model graph itself. Here, this is kind of the core training loop, and then the core kind of validation logic, which is, using very similar APIs to standard PyTorch. And finally, we're expressing here how to access the training and validation data. So we're using the Safar 10 dataset from Torch Vision. So I mentioned there are two inputs to a new workload. There's our model code, which we've just seen, and then a configuration file. So now let's look at a configuration file and the goal of configuration file is just to tell the system what kind of training workload we want to run. So in this case, we're going to start by training a single model with a single, fixed set of hyperparameters. So here we define what those hyperparameters are and what their values are. As I mentioned, the actual choice of hyperparameters is totally arbitrary, totally up to you, but we just want to have a correspondence between the hyperparameters we declare here and then the ones we're using in our model code. The other thing we need to say is the nature of the training workload. So here we're saying we want to train a single model, and we want to train it for 32 epochs worth of training data. So that's all we need to do to launch a new workload. And then now we can create that workload using the command line interface. So the command line interface is called det, and then there are subcommands to do things like start and stop workloads, to examine the state of the cluster, and so on. So if we want to create a new training workload, we do like this. We pass in our configuration file, and then we pass in the model definition. So if we go back to the web interface, we can see now that previously we had one workload training, and now we have a second workload training. Previously had one GPU being used, now we have two GPUs being used. And let's say that actually this previous model that we're training, we don't need that anymore. You know, we want to pause that training, so we can do a non-destructive pause where we are essentially going to checkpoint the state of that model, save it away in case we need it later, and then fairly shortly that GPU will be free for other workloads to use. So we can see here now that this is the workload we just created. It has already been scheduled in the cluster. And if we look at the logs for that workload, we can see now that it's started training. So we're feeding batches of training data in and training the model automatically. We can see in real time, this is the, we're showing here, yeah, the training loss curve. So the model's training away. So great, so that's this, fairly simple example of training a single workload using the system. Let's take a look at how you would do a hyperparameter search. So as I mentioned before, we've already declared the hyperparameters that we think are the most relevant for our model. And in the first workload that we launched, we specified constant values for each of those hyperparameters. Suppose we want to go ahead and do a search over the space of, over a larger hyperparameter space. So we do that with exactly the same model code. We don't need to change our model code at all. We just give the system a different configuration file. So first, rather than specifying constant values for each of these hyperparameters, we instead specify a range of values. So we're going to look at different dropout percentages, different batch sizes, and different learning rates. The second thing we need to say is for the search itself, what algorithm do we want to use to explore the hyperparameter search space, and how many resources, essentially how long do we want to perform that search for. So the system supports a number of hyperparameter search algorithms, random search, grid search, population-based training, but the algorithm we recommend for most use cases is what we call adaptive search, which is based on the hyperband algorithm that one of my co-founders, his lab at CMU helped develop. So in this case, we are doing this adaptive search. We want to look at 50 configurations, 50 trials, and we want to train at most for 32 configurations. And so the way that hyperband works is that we're going to basically try all 50 configurations in parallel, and we're going to prune the configurations that do not appear to be performing well, and allocate more training resources, more training time to the configurations that do seem promising. But that whole process of adaptive resource allocation and comparing the performance of these different trials, that's handled automatically by the system. So if we go ahead and we create one of these search workloads, exactly the same process, we just pass in a different configuration file, and the workload will automatically get scheduled. So if we go back to the cluster, we can see that, so first of all, now we have a second workload running. And then we can see that all 8 GPUs are being used. And in fact, because we are willing to train, we configured the system to train up to 16 configurations in parallel at the same time. We're going to go ahead and provision another GPU instance, 8 GPU instance from AWS. So that'll happen concurrently. But in the meantime, we'll start training the model with, or doing the hyperparameter search with the GPUs that we have available. So then we can take a look at, so this is the hyperparameter search workload that we kicked off. So we can see that we have 7 configurations that we started training already. And the system is automatically going to take care of training all 50 workloads eventually, comparing their performance, and pruning the ones that aren't performing as well. So if we go back, I ran a version of this search previously. So and then we can see here, search took about 30 minutes to run. So it's, relatively simple model, relatively small hyperparameter space. And what this graph is showing is that among all those 50 hyperparameter configurations, what we call trials, what was the best validation error over time? So we can see we started off with very bad predictive performance, and we're able to get down to about 0.22 validation error. So if we compare that to the performance that we had with a single configuration, that was at about 0.42. So able to find a substantially higher performing model automatically. And then if we look at this table of all these the configurations that we've trained, we can look at the winning configuration, and we can say here, okay, we can dig into here's its validation performance, we can look at its training loss, we can look at the hyperparameters that turned out to be the most effective. So apparently batch size of 51 along with these other hyperparameters was the most effective choice. And then we can also look at the model checkpoints. So the system automatically manages taking model checkpoints as workloads run. So we can see here that this is the kind of the final checkpoint of the most high of the best performing hyperparameter configuration that was found. So this would typically be something we'd look to use for future experiments or potentially to deploy to production. So if we go back to the cluster, we can see now that we've provisioned 2 more GPU instances, so we have 24 total. And we configured this search to only use 16. So we have this one search, the model we're training with 1 GPU, and then 16 GPUs with this other workload. So final thing to show you is how to do distributed training. So to do distributed training, we don't need to change anything. All we need to do is vary our our experiment configuration slightly. So if we look here, we're going to train a single model configuration. And so that means we're going to pass in fixed values, constant values for our hyperparameters. The only other thing we need to specify is how many GPUs to use. So in this case, right now we have 7 GPUs free. Actually, let's go ahead and we don't need this guy. We can pause this workload. So we should shortly have 8 GPUs free. So let's say we configure this to use 8 GPUs. So we just set that by saying 8 GPUs. And then if we create a new experiment, again, it's exactly the same process, and that will get scheduled on the cluster. So now we can see we have 8 GPUs free, and our additional training workload should start shortly. So that'll take a little while to start up just because we are provisioning that workload automatically. But let's go ahead and pause this. And we can see a previously a distributed training workload that we launched previously that again, same process, and the configuration we used here was with 16 GPUs. The system takes care of all those details of scheduling the workload, running it in parallel, ensuring that all the GPUs are available, and we can see now that our this distributed training workload has started, and we're using 8 GPUs to run it. Perfect. So that was what I wanted to cover in the demo. And that hopefully gives you a sense of how you can use Determined to train a single model, to do hyperparameter search, and to do distributed training. And kind of all of those kind of functionality, all that's kind of available really at your fingertips as a deep learning engineer. You don't need to configure additional kind of infrastructure or deal with setting up additional tools. So now I wanted to move on to a case study, which is how we use Determined to speed up fine-tuning performance of BERT by 15 times. So what we're going to do is we're going to start with a pre-trained BERT model from Hugging Face, and we're going to, our baseline is going to be fine-tuning that model on the squad dataset with a single GPU. And then we'll go from there to using multiple GPUs to do fine-tuning, and then improving our efficiency further. So let's start with single GPU training. So we did fine-tuning for 2 epochs worth of training data, and that took slightly less than 7 hours. So one point about modern NLP is that people, when we talked about how expensive it can be, that kind of training time I gave for GPT, for example, was training the model from scratch, right? Obviously, a lot of people will not need to do that. They'll just need to fine-tune an existing model. But even that can be very, very expensive, right? We've shown here that it can take, almost 7 hours, and that's fine-tuning one model, not even a particularly large model, and with a fixed set of hyperparameters. So when you think about doing this every day on a very frequent basis, doing high parameter search, that time can really add up. And so when we're reporting time here, we're going to look only at training time. So we're going to omit the time taken to load data and to perform validation. So if we're starting with about almost 7 hours of training time, how can we improve? So the obvious next step is to use multiple GPUs. So we're going to use synchronous data parallel distributed training. Under the covers, we're using Horovod, but as a deep learning engineer, you don't need to deploy that or figure out how to use that if you're using determined. We're going to use standard kind of weak scaling, which means we're going to scale the batch size with the number of GPUs. So each GPU is going to be assigned the same partition of the global batch size that is the same size, but the global batch size itself, we're going to scale with the number of GPUs. So we can see here, if we scale from 1 to 8 GPUs, we can make some pretty impressive gains. We can go from just under 7 hours of training time down to about 1 hour if we're training with 8 GPUs. So not perfect scaling efficiency, but not too bad. And again, we're able to do this without changing our model code at all, without provisioning additional infrastructure. This is just something that we can do by just changing our configuration from slots per trial of 1 up to 8. So suppose that we want to go further, right? It still takes us an hour to fine-tune our model. How can we do better than that? So as we distribute our training workload over more GPUs, we pretty quickly run into the fact that distributed training is a very communication intensive problem, right? We are taking a batch of data, splitting it among the GPUs, training on that data, and then the GPUs need to communicate before we can go on to the next batch. So the more work we can do before needing to communicate, typically the better scalability that we're going to see. So obviously one way to do that is to increase the batch size. And that means that the number of examples assigned to each GPU before they need to communicate can increase, which means we can do more work with less communication overhead. But there's 2 challenges we run into there. First of all, training at large batch sizes can hurt convergence, the actual kind of performance of our model. The second is that large batch sizes can exceed GPU memory. So we'll talk about each of those challenges, but let's actually start with the memory consumption challenge first. So let's suppose that once we reach the kind of maximum batch size that we can train on a single GPU, how do we do better than that? Well, there's a technique called local gradient aggregation, which basically means that each GPU is going to do more forward-backward passes before exchanging gradients, before synchronizing. This is essentially a way to effectively train at a larger global batch size without increasing our per GPU memory requirements. And again, in determined, we can do this without any code changes. All we need to do is configure our aggregation frequency appropriately. So our default aggregation frequency would be 1. If we set it to 8 here, that means that we're going to do 8 forward-backward passes before we synchronize between the GPUs. So let's look at our performance. So in this case, we're just showing performance with 2 GPUs, but similar results would hold on a larger set of GPUs. So we can see that as we scale up our aggregation frequency, we're able to reduce the training time because we're reducing the amount of communication overhead. And our validation accuracy is still good up to a point. So with the 2 GPUs and an aggregation frequency of 10, we get reasonable aggregation frequency. But once we try to increase that to an aggregation frequency of 100, our validation accuracy really falls off a cliff. So what do we do there? So the basic problem, doesn't have anything to do with local gradient aggregation. It's just that we're essentially training with a very large batch size in this setting. And it turns out for our model, with the optimizer that we were using, and the learning rate and so on, that effective batch size does not result in good model performance. So how do we deal with that problem? So in general, how model training will be affected by larger batch sizes is problem dependent. And ensuring good training behavior at large batch sizes is a bit of a black art. So there's a lot of kind of heuristics and techniques that people try, but I would say that right now it's much more of an art than a science. So one popular trick is scaling up the learning rate linearly with the batch size. It turns out in this case that didn't actually help. But another trick that we find effective is switching to a different optimizer. So we tried using the R-Atom optimizer. And in this case, we found that that was actually very effective. So we were able to train with an aggregation frequency of 100. So, effectively increasing the global batch size dramatically. And we did see a validation accuracy drop off, but a fairly modest one, even with that very large effective batch size. So finally, let's talk about going from one GPU from one machine to multiple machines. So far we've talked about scaling from 1 to 8 GPUs. That's something you can easily do on a single machine. But suppose you want to throw more resources at training the model faster. So with typical infrastructure, that's a point at which you need to typically need to switch to a different tool. So you can train on a single machine using something like PyTorch or TensorFlow out of the box. But going from one to multiple machines means, adding some kind of infrastructure, Horovod, cluster scheduling, Kubernetes are typically, Kubeflow. Those are all kind of tools that you might turn to. But if you have kind of started working with a deep learning training platform like Determined, this is a very smooth transition to make. You just tell us how many resources you want, and the system will take care of scheduling doing all the kind of multi-machine coordination, scheduling, and actually orchestrating the distributed training process itself. So one thing to keep in mind is once we go from one GPU to multiple GPUs, we're going from intra-machine communication to communicating between machines. So you'll typically see, higher latency and lower bandwidth depending on your network fabric and so on. And we actually found that with the default settings going from 1 to 2 machines actually decreased performance. But we're able to rectify that by bumping up the aggregation frequency. So training with 16 GPUs and with an aggregation frequency of 2, we're able to get down to a training time of 30 minutes and still with a very respectable validation accuracy. So those are the main points that I wanted to cover. Just to recap, I think where NLP development is today, access to massive computational resources really ought to be table stakes. Even if you're just fine-tuning a pre-trained model, being able to access large amounts of compute, apply them to your NLP training tasks in a very easy and seamless way, I think is a really important capability for teams to think about as they're building out their NLP infrastructure. It's very easy to spend more time managing your compute resources than you do actually spending on deep learning or NLP itself. And that's part of the problems we're trying to solve with Determined, is to make it easy, to allow deep learning engineers and NLP engineers to focus on the machine learning task they want to solve rather than spending all their time managing infrastructure. So we built this platform that really integrates what we think as really sort of table stakes capabilities for modern NLP and modern deep learning: hyperparameter tuning, experiment tracking, distributed training, model management, and so on. So Determined's open source. It's available now under an Apache license, and would love anyone's feedback. Would love to have people try it out, and I'd love to hear how well it works for your problems and your team. Thanks very much.